Hello friends, welcome to my YouTube channel Journey with VIJAYKUMAR SHRIVASTAV. Today I am going to present the topic soil-water relationship. Before presentation, little brief about myself. I am VIJAYKUMAR SHRIVASTAV. I have done M.Sc Agriculture with a specialization in Agronomy from Pant University of Agriculture and Technology, Pantnagar, and presently working as a seed professional in one of the M.Sc in seed industry. In this presentation, we will cover various aspects of soil-water relationship. So let's proceed to the presentation. Soil-water relationship. Both soil and water are essential for plant growth. The soil provides a structural base to the plants and allows the root system to spread and get a strong hold. The pores of the soil within the root zone hold moisture which clings to the soil particle by surface tension in the driest state or may fill up the pores partially or fully saturating with it useful nutrients dissolved in water, which is essential for the growth of the plants. The root of the most plants also require oxygen for respiration. Hence, full saturation of the soil pores lead to restricted root growth for these plants. Since irrigation practice is essentially an adequate and timely supply of water to the plant root zone for maximum crop yield is required. The study of the interrelationship between soil pores, its water holding capacity and plant water absorption rate is fundamentally important, which we will study in this chapter. Now we will study about soil water system. Soil is a heterogeneous mass consisting of a three-phase system of solid, liquid and gas. Mineral water consisting of sand, silt and clay and organic matter form the largest fraction of soil and serves as a framework or matrix with numerous pores of various proportions. The void space within the solid particle is called the soil pore space. Decayed organic matter derived from the plant and animals remains are dispersed within the pore space. The soil air is totally expelled from soil when water is present in excess amount that can be stored. Water enters this system through precipitation. It falls to the ground and accumulates in a very thin layer right at the surface. From this thin layer at the surface, the water infiltrates into the soil, where it accumulates in empty pore spaces and utilized by plants. Now we will study about the importance of water in plant growth. Water maintains the turbidity of the plant cells, thus keeping the plant erect. Water accounts for the largest part of the body weight of an actively growing plant, and it constitutes about 85 to 90% of the body weight of young plants and 20 to 50% of older or mature plants. Water provides both oxygen and hydrogen required for carbohydrate synthesis during the photosynthesis process. Water acts as a solvent of plant nutrients and helps in the uptake of nutrients from soil. Food manufactured in the green parts of a plant gets distributed throughout the plant body as a solution in water. Transpiration is a vital process in plants and does so at a maximum rate called the potential evapotranspiration rate. When water is available in adequate amount. If soil water is not sufficient, then the transpiration rate is curtailed, seriously affecting plant growth and yield. Leaves get heated up with solar radiation and plants helps to dissipate the heat by transpiration, which itself uses plant water. Sources of water. Water covers 71% of the Earth's surface. It is vital for all known forms of life. On Earth, 96.5% of the planet's crust water is found in seas and oceans, means that is surface water, 1.7% in groundwater and 1.7% in glaciers and the ice caps of Antarctica and Greenland. A small fractions in other large water bodies, 0.001% in the air as vapor, clouds and precipitation. Only 2.5% of this water is fresh water and 98.8% of water is in ice and groundwater. Now we will discuss about different sources of water. First one is surface water. This is water that is open to the atmosphere and results from overland flow. It is also said to be the result of surface runoff. There are four major sources of surface water like rivers, lakes, ponds and tanks in the country. Surface water is water in a river, lake or freshwater wetlands. Surface water is naturally replenished by precipitation and naturally lost through discharge to the ocean, evaporation and subsurface seepage. Although the only natural input to any surface water system is precipitation within its watershed, the total quantity of water is that system at any given time is also dependent on many other factors. These factors include storage capacity in lakes, wetlands, and artificial reservoirs, the permeability of the soil beneath these storage bodies, the runoff characteristics of the land in the watershed, the timing of the precipitation, and local evaporation rates. All these factors also affect the proportions of water lost. Second source of water is groundwater. This is considered to be water that is below the earth crust but not more than 2500 feet below the crust. Water between the earth crust and the 2500 foot level is considered usable fresh water located in the pore space of soil and rocks. It is also water that is flowing within aquifers below the water table. Groundwater is obtained from the following: wells and springs that are not influenced by surface water or a local hydrologic event. Third source of water, rainwater. Collecting our own rainwater is an excellent way to conserve this precious resource. A basic rainwater collection system catches rainwater from our roof or other surfaces and channels it into a container for storage. Rainwater itself is generally clean, but it can pick up microorganisms, pollutants, and debris when it hits our roof. That is why systems for rainwater used inside our home often include filtration or other treatment for safety. Outdoor rainwater collection systems don't need as much treatment because the water is typically used outside. Now, fourth source of water is frozen water. Several schemes have been proposed to make use of icebergs as a water source. However, to date, this has only been done for novelty purposes. Glacier runoff is considered to be surface water. The Himalayas, which are often called the roof of the world, contain some of the most extensive and rough high altitude areas on earth, as well as the greatest area of glaciers and permafrost outside of the poles. 10 of Asia's largest rivers flow from there, and more than a billion people's livelihoods depends on them. Now, fifth source of water is under river flow. Throughout the course of the river, the total volume of water transported downstream will often be a combination of the visible free water flow together with a substantial contribution flowing through subsurface rocks and gravels that underlie the river and its floodplain called the hyporheic zone. For many rivers in large valleys, this unseen component of flow may greatly exceed the visible flow. Now we will study about absorption of water in soil. This is also called entry of water into the soil. First one is infiltration. Infiltration refers to the downward entry or movement of water into the soil surface. It is a surface characteristics and hence primarily influenced by the conditions of the surface soil. Soil surface with vegetation cover has more infiltration rate than bare soil. Warm soil absorb more water than colder ones. Coarse surface textures, granular structure, and high organic matter contents in surface soil will help to increase infiltration. Infiltration rate is comparatively lower in wet soils than dry soils. And what are the factors affecting infiltration? First one is clay minerals, second is soil texture, third is soil structure, fourth is moisture content, fifth is vegetative cover, and fifth is topography. Now, what is infiltration rate? An important measurement of soil water movement is the rate at which water enters the soil surface is called infiltration rate. The value is an indication of the potential for erosion or water runoff, an event which seldom occurs with a turf covered surface. Under field conditions, localized ponding may occur after heavy rains if the infiltration rate is low. Second type of absorption of soil water is percolation. The movement of water through a column of soil is called percolation. In percolation, when the soil profile is wetted, the movement of more water flowing through the wetted soil. This is important for two reasons. This is only source of recharge of groundwater, which can be used through wells for irrigation. And second, percolating waters carry plant nutrients down and often out to reach out of plant roots. Means this is called leaching. And what is permeability? Permeability indicates the relative ease of movement of water within the soil. The characteristics that determine how fast air and water move through the soil is known as permeability. In this diagram, we have shown the water movement to the soil like surface flow runoff, infiltration, percolation, and leaching. will discuss about soil water movement. It is of three types. First one is saturated flow, second is unsaturated flow, and third is water vapor movement. There are three factors which are responsible for soil water movement. First one is gravity, responsible for downward movement. Second is adhesion, which is the link between soil particles and water, and third is cohesion, which is the linkage between water and water. Adhesion and cohesion principal forces that move water in unsaturated soil. First, water flow is gravitational flow or saturated flow. This occurs when the soil pores are completely filled with the water, when the moisture content of the soil rises above field capacity. This water moves at water potential larger than minus 33 kPa. Flow of water by gravity pull is important in the rapid removal of excess water and the return of air to the system. Gravitational flow occurs in the micropores of the soil. When gravitational flow is restricted, it is necessary to install artificial drainage system. Removal of gravitational water, however, doesn't remove any water of value in the production of crops and grasses. It begins with the infiltration, which is water movement into soil when rain or irrigation water is on the soil surface. When the soil profile is wetted, the movement of more water flowing through the wetted soil is termed percolation. Second movement of water is capillary flow or unsaturated flow. The flow by capillary force is through the micropore. Capillary flow is the movement of water at moisture content of field capacity or less. It is flow of water held with water potential lower than minus 1 by 3 bar. Water will move towards the region of lower potential. In a uniform soil, this means that water moves from wetter to dry areas. The water movement may be in any direction. The rate of flow is greater as the water potential gradient increases and as the size of water filled pores also increases. The two forces responsible for this movement are the attraction of soil solids for water, means adhesion, and capillarity. Under field conditions, this movement occurs when the soil micropores filled with air and the micropores filled with water and partially with air. Third soil water movement is water vapor movement. It is of two types. First is internal movement. In this movement, the change from the liquid to vapor state takes place within the soil, that is in the soil pores. And second is external movement. The phenomenon occurs at the land surface and the resulting vapor is lost to the atmosphere by diffusion and convection. When soils are unsaturated, some of the pore space is air filled and water moves through the pore space as vapor. The driving force is the difference in water potential is expressed by differences in vapor pressure. Generally, vapor pressure is high in warm and moist soil and low in cold and dry soil. Now to study soil water constant. The soil water constants are considered based on the extent to which the water is attached to the soil particles and size of pores. First one is field capacity. It is the capacity of the soil to retain water against the downward pull of the force of gravity. At this stage, only micropores or capillary pores are filled with water and plants absorb water for their use. At field capacity, water is held with a force of 1 by 3 atmosphere. Water is at field capacity is readily available to plants and microorganisms. It is the amount of water that remains 2 to 3 days after the saturation of a soil with water. Second is permanent wilting point. The stage at which plants starts wilting for want of water is termed as wilting point, and the percentage amount of water held by the soil at this stage is known as wilting coefficient. It represents the point at which the soil is unable to supply water to the plant. Water at wilting coefficient is held with a force of 15 atmosphere. It is the lowest amount of water that is held in the soil and which plants are unable to use. Third soil water constant is available field capacity or available water capacity. The amount of water required to apply to a soil at the wilting point to reach field capacity is called the available water. The water supplying power of soils is related to the amount of available water a soil can hold. The available water is the difference in the amount of water at field capacity and the amount of water at the permanent wilting point. It is considered as water available for a plant to extract from the soil moisture zone. Now fourth soil constant is hygroscopic coefficient. The hygroscopic coefficient is the maximum amount of hygroscopic water absorbed by 100 gram of dry soil under standard conditions of humidity at 50% relative humidity and temperature of 15 degrees centigrade. This tension is equal to a force of 31 atmospheres. Water at this tension is not available to plants but may be available to microorganisms. Fifth soil water constant is maximal water capacity. It is also known as maximum retentive capacity. It is the amount of moisture in a soil when its pore spaces, both micro and macro capillary, are completely filled with water. It is a rough measure of total pore spaces of soil. It is the maximal water content of soil by total water saturation. Now, sixth soil water constant is air capacity. It specifies the size of the drained macropore spaces. The water percolating in the soil has flown downwards and is not available for the plants anymore. It coincides with the size of the pore spaces that is filled with air at the field capacity conditions. Now, seventh soil water constant is total pore volume. This is the amount of all cavities in soil which is expressed in volume percent. Now we will study about forms of soil water. First one is gravitational water. Form of water which reaches at the soil water table due to the gravitational force after the rainfall. This form is not available to plants but available by mechanical methods or by tubewell irrigation. A soil sample saturated with water and left to drain the excess out by gravity holds onto a certain amount of water. This volume of water that could easily drain off is termed as gravitational water. This water is not available for plants use as it drains off rapidly from the root zone. Second is capillary water. Water exists between soil particle in a small capillary pores is called capillary water. It is the most common available form of water for absorption. This is the water content retained in the soil after the gravitational water has drained off from the soil. The water is held in the soil by surface tension. Plant roots gradually absorb the capillary water and thus constitute the principal source of water for plant growth. Third one is hygroscopic water. Thin film of water is tightly held by the soil particle is called hygroscopic water. This water is also not available to the plants. This is the water soil absorbs when exposed to moist air. This is called as hygroscopic water. It is held as a thin film over the surface of the soil particle and is under tremendous negative pressure. Here we have shown the diagrams of different waters like hygroscopic water, capillary water and gravitational water and the attachment between soil particles and water molecules. Next soil water is chemically combined water. The amount of water present in chemical compounds which are present in the particles of soil. This is not available to the plants. Now last one is atmospheric humidity. This is water vapor present in air which can be absorbed by hanging roots of the epiphytes due to the presence of spongy velamen tissue and hygroscopic hairs. Now to study factors which are affecting availability of soil moisture. First one is climate, under which there is main precipitation and temperature. The topography, which is the arrangement of the natural and artificial physical features of an area. Third is elevation, which refers to a height of a hill. And then slope, degree to which a surface is tilted. Then soil properties like water table, hard pan, water holding capacity, soil composition, soil profile, soil texture, soil structure and organic matter of the soil. And then vegetation type and vegetation age. And then this is the including the root system of the plant. So these are all the factors which affects the soil moisture availability to the plants. Now we will study about water absorption by plants. Water is absorbed mostly through the roots of plants, though an insignificant absorption is also done by leaves. Plants normally have a higher concentration of roots close to the soil surface and the density decreases with the depth. In a normal soil with good aeration, a greater portion of the roots of most plants remain within 0.45 meters to 0.6 meters of surface soil layers, and most of the water needs of the plants are made from this zone. As the available water from this zone decreases, the plant extracts more water from lower depth. When the water contents of the upper soil layers reaching wilting point, all the water needs of plants are met with the lower layers. When the top layers of the root zone are kept moist by frequent applications of water through irrigation, plants extract most of the water, about 40% from the upper quarter of their root zone. In the lower quarter of the root zone, the water extracted by the plant meets about 30% of water needs. Further below, the third quarter of the root zone extracts about 20% and the lowermost quarter of the root zone extracts the remaining 10% of the plant's water. It may be noted that the water extracted from the soil by the roots of a plant moves upward and essentially is lost to the atmosphere as water vapors mainly through the leaves. This process called transpiration, resulting in losing almost 95% of water sucked up. Only 5% of the water pumped up by the root zone system is used by the plant for metabolic purpose and increasing the plant body weight. The factors affecting absorption of water by roots. First one is available soil water, concentration of soil solution, soil air, soil temperature, transpiration, absorbing root systems, metabolism and association of mycorrhizas. This is the association between fungus and roots which enhance the absorption of water. Now we will study about evaporation. The change of state of water from solid and liquid to vapor and its diffusion into the atmosphere is referred as evaporation. Evaporation is an important process of hydrological cycle. The evaporation from the soil is an important factor deciding the irrigation water requirement of a crop. In modifying the microclimate of a crop, the evaporation from the soil is an important factor. Now we will study about factors which are affecting evaporation. First one is environmental factor, in which water temperature. With increase in temperature, there will be increase in evaporation. Second is wind. The evaporation will increase with increase in wind velocity. Third is relative humidity. The evaporation is high at low relative humidity and less at high relative humidity. Fourth is atmospheric pressure. The evaporation is more at low pressure and less at high pressure. And second factor is water factors, in which first one is composition of water. If there are dissolved salts and other impurities, then there will be reduction in evaporation. And second is area of evaporation. The larger the area of exposure, there will be greater evaporation. Transpiration. Most of the water absorbed by plant is lost to the atmosphere. This loss of water from living plant is called transpiration. It can be stomatal, cuticular or lenticular. It plays an important role in dissipation of radiant energy by plant parts, translocation of water in the plants and translocation of minerals in the plant. Now the factors affecting transpiration. First one is environmental factors, in which first one is light. By directly opening and closing of the stomata, there is periodicity in transpiration rate. Indirectly, by increasing the temperature of leaf cells, the transpiration is increased. Second is atmospheric humidity. The rate of transpiration is almost inversely proportional to the atmospheric humidity. Then air temperature. Increase in temperature results in opening of stomata, which in turn increase transpiration. And then fourth is wind velocity. The higher the wind speed, higher the transpiration. Second factor is plant factors, in which first is plant height. Water needs for the crops having the variance in height. Then leaf characteristics. Reduction in leaf area brings reduction in transpiration. Then third is availability of water to the plant. If there is little water in the soil, the tendency for dehydration of leaf causes stomatal closure and a consequent fall in transpiration. Evapotranspiration. Evapotranspiration denotes the quantity of water transpired by plants plus moisture evaporated from the surface of the soil. As long as the rate of root uptake of soil moisture balances the water losses from the canopy, evapotranspiration continues to occur at its potential rate. When the rate of root water uptake falls below the transpiration demand, actual transpiration begins to fall below the potential rate. This is either because of the soil cannot supply water to roots quickly or the plant can no longer extract water to meet the evaporation demand. Now to study factors affecting evapotranspiration. Those factors which are affecting water supply like soil storage capacity, rainfall and irrigation. Other factors which are affecting energy supply, then light, temperature, relative humidity, wind and plant characteristics like root shoot ratio, leaf characteristics and thick cuticle. All these factors will affect evapotranspiration. Consumptive use of water. It is the quantity of water used by the vegetation growth of a given area. It is the amount of water required by a crop for its vegetated growth to evapotranspiration and building of plant tissues plus evaporation from soils and intercepted precipitation. It is expressed in terms of depth of water. Consumptive use varies with temperature, humidity, wind speed, topography, sunlight hours, methods of irrigation and moisture availability. Consumptive use is equal to evaporation plus transpiration It is expressed in terms of depth of water. Now to study types of consumptive water use. These are of three types. First one is optimum consumptive use. It is the consumptive use which produces a maximum crop yield. Second is potential consumptive use. If sufficient moisture is always available to completely meet the needs of vegetation, fully covering the entire area, then resulting evapotranspiration is known as potential consumptive use. Third is seasonal consumptive use. The total amount of water used in the evapotranspiration by a cropped area during the entire growing season is termed as seasonal consumptive use. The factors which are affecting consumptive use of water. First one is evapotranspiration, which depends on humidity. Second is mean monthly temperature. Third is growing season of crops and cropping pattern. Fourth is monthly precipitation in that area. Fifth is wind velocity in locality. Sixth is soil and topography. Seventh is irrigation practices and methods of irrigation. And eighth is sunlight hours. Here to study effective rainfall. Effective rainfall means useful or utilizable rainfall, which can be defined as the portion of the total annual or seasonal rainfall which is useful directly or indirectly for meeting the crop water needs in the crop production at the site where it falls, but without pumping. Effective rainfall or precipitation is equal to the difference between total rainfall and actual evapotranspiration. At ground level, water from effective rainfall is split into two fractions: surface runoff and infiltration. Effective precipitation is the amount of precipitation that is actually added and stored in the soil. As with total rainfall, effective rainfall is expressed in height in millimeters related to a unit of time or in volume. The factors which are influencing effective rainfall. First is rainfall characteristics. Second is land characteristics. Third is soil characteristics. Fourth is groundwater characteristics. And fifth is management practices. And sixth, crop characteristics. So these factors will relate to influencing effective rainfall. Now to study hysteresis. The moisture content at different tensions during wetting of soils varies from the moisture content at same tensions during drying. This effect is called as hysteresis. This is due to the presence of capillary and non-capillary pores. The moisture content is always low during sorption and high during desorption. Hysteresis phenomenon exists in soil minerals as a consequence of shrinking and swelling. Shrinking and swelling affect pore size on a macro basis as well as on the basis of overall bulk density. This was all about soil and water relationship. Now my presentation ends here. Thank you very much. See you again shortly. I have given here my YouTube channel details, Journey with VIJAYKUMAR SHRIVASTAV. Having request, please visit the channel, subscribe it, and please provide your kind and valuable feedback for further improvements. Thank you.